difficult in general because people must have their lunch, and then it's difficult to keep them awake. So the speaker has a important and bigger role here. But before I proceed, let me thanks both the organizer for this, particularly Professor Avasthi, for giving me the opportunity to present some of the work that we have been doing in this area in research. But this is more from a broader perspective, where I have tried to put things which will fall in line as per the mandate of this FDP. So before I go, let me give you some outline of my talk. So we'll be discussing something about, we'll have introduction, then I will try to discuss with you why such type of systems, high resolution systems, are required in different area of like physics, biology, medicine, or engineering. So we'll be covering on some of these aspects, and then how it can be utilized for example for aerospace, where you can monitor some micro crack, which are more of an engineering problem, and then also how one can develop such type of highly sensitive systems for traffic monitoring. So quickly go back to some of the requirement that why one requires a high resolution sensing. So it is more important here that if you want to detect anything, now detection of anything can happen either in a space or in time, or we can also do using some spectral interrogation. Now, what do I mean by space? For example, our eye can resolve the resolution of our eye is something you can say that 0.1 maximum it can be, not 0.1, I should say. Resolution of our eye is 1 millimeter. For example, if I give you a scale and ask you to resolve two lines separated by 1 millimeter, you will be able to do so. If you have a very good eye, possibly, then you can also do 0.1 millimeter resolution. But if I give you some scale which is, let's say, 0.01 millimeter separated, 2 points separated by 0.01, two lines separated by 0.01 millimeter, you will not able to do that. So that's the typical way you can say that how you can resolve the 2 points in a space, like in this case the scale on the line. Now the temporal resolution is something where how much in time wise you can resolve. So if I ask you that can you see, you look into your watch or the clock, possibly not watch, some watch may not have these hour and second hand. So but in clock you will have mostly these most of the clock have those hour and second hand, especially the one in my office has that. So if I ask you that what best you can resolve, so you will say, sir, I can resolve 1 second. So the second needle moves by 1 second, I can make out. If I ask you that if I divide that further into 10 points, can you measure some point 1 second? You will struggle. You will struggle, but very good I may do. But if I divide into further, uh, I divide, then it will be difficult for you to measure. So you can say that the resolution in terms of time for our eye is 1 second. Spectral details are, for example, if I tell you that uh, you can distinguish between red color and orange color. Both are largely giving you some sort of a I should say similar type of color. It is not like that blue and red which are completely distinct. Red and orange are close by. But now uh, if I ask you that can you distinguish between red apple and red tomato. So you can distinguish tomato and you can distinguish apple, but sometimes you may have the similar type of red in color. Now, this is what is called as a spectral resolution. What I'm trying to tell you here is as follows, that even the red color as such has many different shades of red. So best example, if you go to a, especially for the other gender, if you see when they go to buy a lipstick, they will have, the shopkeeper will provide them with minimum 10-15 shades of, let's say, red or pink in color. Now all these shades are different, they know better which shades is what. But as a physicist or as a technical person, you can always say that no, this shade is different than the other shade and stuff. So what difference is there? The difference is in their wavelength, what we are able to perceive. So that is what is called as a spectral details. Now how good we can resolve these space time or spectral details is what you can tell it as a high resolution, uh, or high resolution sensing, for in this case example. Now these high resolution sensing, uh, it depends on some of these parameter as I discussed. But if I ask you that, these all you can discuss, like spatial, temporal, or spectral, you can discuss. But at quantum level, you will struggle. Why quantum level you will struggle? Because things happen at quantum level. Only those things happen which are something like, you can say, which you cannot see with your eye. And therefore, quantum level systems are difficult to manage. You can't manage quantum level systems with your eye, but of course you require them, and as we go ahead with the talk, you'll see why it is required. So to do this high resolution uh, measurement or high resolution sensing, these are some of the techniques which are enabler. Now techniques, when we say, these are either you can have optical techniques or you can have an electronics technique. So optical techniques uses properties of uh, properties of, let's say, electromagnetic wave or transverse waves like light waves. So they uses the property of light waves. Electronics uses the concept of current and voltage. Hybrid technology can be both, the one which can use the concept of electronics, which is like electron and photon, both are involved in the as a technique which enable. And then there is a quantum technique. Now quantum technique is based on the concept, which is something like, it is based on the concept of superposition principle, that if you want to measure something quantum mechanically, that you may have heard this like many times, that the state collapses and stuff. What I'm trying to tell you is, it is this technique which is only valid for systems at atomic and subatomic level, and for them you require a special type of measurement, which basically comes from superposing two wave function. So in quantum mechanics, a concept is called is a wave function, which can which through which you can basically write. So through which you can basically uh, note. This is a notation. Wave function is some sort of a notation which allows you to. Wave function as such will not give you the complete picture, but if you take the complex conjugate of this, then it's able to tell you some sort of a probability that whether an electron can be present there, or let's say atom can be present there or not. So quantum mechanics is basically, as a technique, it enables you to do the measurement at atomic and subatomic measure level. But please note, unlike many of these techniques which are deterministic, quantum mechanics is a probabilistic technique. It always tells you the probability. It will never tell you, going to confirm you that no, this is what will going to happen. Unlike a classical systems, where that if I give you the initial position and momentum of some system, so you can always calculate that after so much time, what will be the velocity, or what will be the momentum, or what will be the energy of a given system. In quantum mechanics, you can always say that the probability of this is going to be so much. Not so. Therefore, quantum based techniques which are utilized are basically a probabilistic technique. So if you see carefully, that in case of engineering, you see where high resolution systems are required. So for example, as I told you, if you see this, the one which I am showing you is basically some sort of a you can say semiconductor, on which some scratch or some holes are there. And you see that these are some sort of a defect. It is not plain, there is something which is coming up here. So these are very high resolution. We are talking about some 20 nanometer defect on some silicon wafer, something like that. Or if you want to make some sort of a grating here, you see that these are lines or some sort of a structure you want to see. Ideally, these should have been plain line, but you see it form a pattern of a H. That means these two get connected. Now, these are basically defects. So what is required for engineering is to do very high level of technology or engineering. You require systems which should able to inspect these wafers at nanometer device, so that device at nanometer scale, so that a device can be fabricated properly. This shows you some sort of a bridge, as you can see here. So in this bridge, you see there are some sort of a cable. You can see it is being wrapped around. So these cables basically can be utilized to identify if there is some crack in this bridge. Now those cracks will be some micro crack you cannot see with your eyes. So those cracks need to be identified. So there are techniques which are based on largely on a scattering. So you send some pulse through some optical fiber, and depending upon some sort of a scattering, which can be scattering is of different type. You know that there are Raman scattering, there are Brillouin scattering, there are Rayleigh scattering. So depending upon the nature of the crack, one can use one of these scattering phenomena to identify some micro cracks in the bridge. Now these are high resolution engineering based problem which need to be addressed. Similarly for biomedical, if you have some sort of a tissue, you can see that if you have some tissue and if there are some microfluidics over that, you can see that there are some microfluidics going on. And if you want to image them, you require some sort of a high resolution biomedical engineering. Similarly, in area of mechanical engineering, so you can see that nowadays most of the things are getting into AI based. So AI is some tool which operates on large data, but then you require some systems which are largely, for on bigger scale, these are, mechanical systems, but on a smaller scale, people also use uh, MEMS based systems where, you can, if you want to precisely place some sort of a, any fluid or any item on a small using some sort of a robotic arm to which some sort of uh, uh, caliper is attached, then you would require for automations of these precise positioning of some of the items, or to control them, you require some sort of a high resolution system. So similarly, if you see where the high resolution systems come into in case of physics, so you'll realize that now this high resolution system in physics can be broadly divided into either you do quantum physics. So you basically in quantum physics you require some sort of a detection unit is required. So this is a standard systems which nowadays are also to some extent commercially available. So what does this system shows you? It shows you some up conversion crystal. These are non-linear crystal. You pump with some laser, and then you try to create these blue dots with white as center. These are single photon. You try and you put a beam splitter there, and you split this single photon, and using two of these APDs, which are called as avalanche photodiode. So basically you detect these two photon, and then you try to correlate them. So you get some correlation peak like this. So these are some quantum physics based high resolution systems which are utilized. In astronomy, most of you are aware that in the whole world, the most sophisticated device that has ever been built by a human being is LIGO. And this is a example. This is a diagram which I'm showing you for the LIGO, where it is based on the concept of interferometry. And these are very, very high resolution system. How high is high? We are talking about these systems can resolve displacements or measurement in terms of length of order of 10 raised to power minus 23, minus 25, and beyond that. Similarly, if you want to do some optics-based systems, this is what is called as a near-field imaging. Means to say that you want to image something with very, very high resolution. Then the people have been using some amount of advanced concepts like plasmonics to do these imaging technique. Then you do a lot of condensed matter based physics where you try to probe materials property using materials property using some of the plasmonic structure. Like here you can see you are taking some sort of a nanoparticle, or these are some thin film, where you can see that you are able to excite some sort of a wave at the interface of metal and dielectric. These are called as a plasmon wave. And if you take the nanoparticle, then you can have basically, you can have a field which get something like that. If you apply electric field to some nanoparticle, you see that electrons and holes get separated out in different direction. So these basically then form some sort of a hotspot. You get a lot of electric field around these nanoparticles. What I'm trying to tell you is that high resolution sensing is something which is must across all discipline, whether it is science or whether it is engineering. So let me focus more on optical based system. Why optical based system? You have to come to, again, you have to come to this line. You see, even while being in quantum or in classical system like astronomy, where high resolution telescope you are using, please note all these systems, whatever I have shown you here for high resolution systems, all these are light based technology. The LIGO, what you are talking about, the most precise instrument ever been made by humankind, is also based on optics. So it's based on interferometry. Therefore, I will be focusing more on optical systems, which are basically utilized to make very high resolution device. So if you want to make any optical sensing systems, you require basically 4 unit. You require some light source. Now these light source can be, you can have a light source which can be both a laser source, or it can be LED source, or it can also be tungsten halogen source. So you can use any of the light source. What will decide what you will going to use? It will get decided by what you are interested to sense. So light source can be laser source, which are coherent source. It can be LED, partly coherent source. Even the tungsten halogen lamp, like you can use, or white light as a non-coherent white light source can also be utilized. Then what you require is a sensing probe. That means what you want to sense with high resolution is something which is the sensing probe. So whenever you have a light which gets through the sensing probe, the property of the light changes. So the different property that are associated with the light, for example, the wavelength of the light, the polarization of the light, the frequency of the light, the intensity of the light, the orbital momentum associated with the light. Now, this is something new which we'll be discussing. Light has some angular or orbital momentum. So that also even changes if you suitably put them on certain system. So that can also be utilized. And then whatever the change in the light properties there, in the presence of this sensing probe, you basically detect them. Once you detect them, then of course you have to process it. You have to process it to show that, what you are trying to detect. Please note, when we are talking about high resolution, we are basically talking about some sort of a sensors and actuators. So this is a general global sensor market. What I'm trying to show you here, this is slightly oldish data, which is 2023, but you can check from here how these data are basically translating on. So, but the market size is quite big. So you see, what we have tried to show you here is the way high resolution sensing market is divided for consumer electronics, automotive and transportation, healthcare, aerospace and defense, manufacturing sector, energy utility, and others. So this is where the sensors are largely utilized. And as you can see that it's showing that in all the coming days, this high resolution sensing will be the requirement for people. And this is what I was trying to show you here, that where all these systems are basically utilized. You talk about anything, manufacturing sector, infrastructure, healthcare, security, transportation, environment, you talk any of these items or any of these area, and you require some sensing systems. So if you are using optical sensing systems, it is expected that they will going to give you very high resolution. And this is the motivation for this today's talk. So I was talking with you about optical sensing systems. So optical sensing systems, these are the principles, the key features, where it can be utilized, and the sensing principle. So these two, you can say, these are sensing principle. This is principle in general. So if you take any light, So the property of light get modulated as I told you about the phase, wavelength, intensity, polarization due to any external measurement field. So if you apply any field, any external parameter, and if the property of light get changed due to that parameter, then you can detect that parameter in terms of the light property. This is what it means. So that light property allows you to do sensing either by modulating the intensity or modulating the wavelength or modulating the phase or the modulating the polarization. So you can modulate the external parameter, can modulate uh, I should say one of these property of light, and that you can detect for identifying that external parameter. The important aspect is that all these sensors, high resolution, should be highly sensitive, should have high dynamic range of detection. That means it should operate over a broader wavelength range. Now, these also optical sensors has advantage that these are largely immune to electromagnetic interference. Unlike the electronic sensors, where electron interact with the electromagnetic field, light, being itself electromagnetic wave, it's immune to those. And also these are, these can, one can make a device which can operate over high temperature. The other advantage of using optical systems are these are multiplexable. So when you say multiplexable, basically you can multiplex them, you can put too many sensors together, and then you can also try to, remotely operate them. So these are also, since they uses some of the material which are abundantly used, therefore these are economical in nature. What you can do with these optical systems, you can measure any parameter, whether it is physical parameter like temperature, pressure, curvature, and dynamic field, or chemical element like environmental pollution, gas and mineral, or biological like protein and biomolecule. So these are the advantages that using optical systems, you can develop a very high resolution sensors based on one of these, based on one of these modulation technique, and it can detect any of these parameters. So just this diagram, this particular plot, I thought that I will tell you about, some of the biological based sensing which people have, utilized for detection. But it is not only optical, but other techniques also, like electrochemical or calorimetric or piezoelectric, and then there you have all bunch of optical techniques. Please note, please note that some of these techniques are whatever it has been shown here. These are also, they have been utilized using this calorimetric and electrochemical. But as I mentioned to you that these are some of the advantages or key features of electrical optical based systems, and this is what makes it different than the electronics based system. So let me discuss with you some of the way in which you can detect these, some of the ways in which you can detect these biochemical, or you can do biochemical sensing. It is as follows. So the biochemical sensing you can make, now you can make, you please note that I told you that LIGO is one of the most, LIGO based on interferometry is one of the most sophisticated systems which can do very high resolution sensing. So interferometric as such is a technique. One of interferometric is most versatile and most sensitive technique in optics, and therefore I am talking about some of the interferometry and how one can make those interferometry using some optical fiber. This is what I'm trying to show you. So you take some optical fiber, and then you can have reference arm, you can have sensing arm, you can use some coupler to couple the light into these two, and then you can collect them. So these some of these are shown here. One is, you can make some sort of a magenta interferometer. Then you know uh, in another case, you can make some, you see, optical fiber consists of central core and the cladding, so you can mismatch the core. So core you can misalign, and then you can use it. Another technique is what is called as, you use a specialty fiber, where you try to use two types of fiber and then you excite the cladding modes. This is another way to do that. Then people also use a lot of MMF, what is called as a multi-mode fiber. And then there are no core fiber or thin core fiber, and then of course you can make tapered fiber. Please note, what we are trying to do in all this configuration is as follows. We are, that to interfere or for interference, for interferometry based technique, you require two arm. you require two light in two arm. One is sensing arm, another is reference arm. Through all these technique, we are basically trying to create two-arm interferometry, and this is what is shown. And these are the ways in which you can create two-arm interferometry. So once you have one of these, one of these systems, which are basically MZI, these are Mach-Zehnder systems, then you can use it for sensing application. Another systems that I use are in form of a Michelson interferometer. Here, what you do, here all these things are in transmission, so you get as an output. But in case of a Michelson interferometer using optical fiber, you get at the same end. So these are all point probe where you coat this surface basically, and if you incident input light, it goes through here. Now this input light excites the core mode and the higher order cladding modes, and these two modes basically interfere, and it gives you some nice interference in the output. But you get the interference on the same side as that of the input. Then there is another type of interferometer. This is Mach-Zehnder, this is Michelson. Then another type of interferometer is called as a Fabry-Perot interferometer. So you basically have to create some sort of a cavity, and these are two sort of mirrors, and you create cavity. Now these reflecting surfaces or mirrors and cavity in between can give you a good nice interference pattern again. People also use, they do a lot of biosensing by using some sort of a biolayer. So basically what they do, they functionalize this Michelson interferometer with some biosensing layer. And whenever they analyze, these will try to bind them. The phase that get accumulated by the two beam changes. And this change in the phase accumulation is how you try to identify what analyte has bounded to that. So these are some of the interferometric system for biochemical. Let me show you one of them. One is using SMF and or PCF. So this is what you can see here. So you can see that this is in reflection. You get a very nice interference pattern. So how these interference pattern are formed here? These interference pattern are formed because if you take a standard single mode fiber and you take a specialty fiber like this, then you can join them suitably. And once you join them, so you basically excite the core mode. These are the core modes. These are diagrams which can be generated using finite element method. So you can excite the core mode. You see there is a light in the center, and you can also excite the higher order cladding modes. So cladding modes are the modes which are supported at the cladding and air interface. So these are the higher order cladding modes. You excite them. So you see LP11, LP12, LP. These are all modes of a specialty fiber. So what will happen? Either this will interfere with this, or this will interfere with this will interfere with this, or this will interfere with this, or this will interfere with this will interfere with this will interfere with this. So a different possibility in which interference can take place. And if you plot them, then you can see that what is here is a reflection versus wavelength. You get a very nice interference pattern. These get governed by basics equation. You don't have to really worry. What is important here is that you see this is delta lambda m. That is change in the wavelength. This is your wavelength axis. This is your intensity, reflected intensity in dV. The change in the wavelength for sensing, I am saying the change in the wavelength. So if you have, let's say, if you make this device in air, you get some interference pattern like this. But if you dip this in water, which has a different refractive indices, then this interference pattern will going to change. So you see the change in the wavelength basically depends upon what is the length of this interferometer. Here in this case, L is 12 mm. Delta N effective is the effective index difference between the core mode and the excited mode, higher order cladding mode. So this is delta N effective. So it depends upon the change in wavelength of these. How much the wavelength will shift will depend upon what is the length and what is the core refractive index difference between the refractive indices of core and cladding mode. So the same system, the one that I have discussed with you, one can utilize for the detection of environmental pollutants. This environmental ammonia is one of our environmental pollutants. So please note, what we are trying to discuss here is how to make a high resolution sensors which can be utilized for biochemical detection or for physical detection, or for let's say engineering, addressing the engineering problem. So what I'm trying to show you is how one can determine some of the problems like environmental problems. So what we have taken here, this is SMF, is called as a single mode fiber. So you take one single mode fiber, you put some sort of a specialty fiber or PCF. These are called as a photonic crystal fiber. So what happens, you incident some light at this junction where the SMF and PCF joins. There is some area. Now the length of this area is around 140. The length of this where they to join, they form some solid region, and this length is around 140 micron. So once you incident a light, what happens? The light hits this solid region, and it, after hitting, what happens, that it diffract. You know that whenever the wavelength of the light is comparable to the dimension, which is comparable to the wavelength, light diffract. So we are basically coming with 1.5 micron, and this is 140 micron. So the fundamental mode of the light which get coupled, you see here, this is a light, it get coupled here, so it diffract. Now as it diffract, it also broadens. So you see it is getting diffracted and broadening, and as it broadens, it moves through the core, and also it moves to the cladding. So as it moves from the core and cladding, again it combines. So the light which is coming from the core and the light which is coming after interacting with the cladding, they have different velocity. The light which will go through the core will have different velocity. The light which will go through the cladding will have different velocity. Now, since they have different velocity, they will going to accumulate different phase difference, because please note, the phase is there in k equal to 2 pi by lambda times n effective. So phi, how you define phi? It is how much length it is covering, and what is the accumulation in the phase is basically given by what is the velocity in this region, what is the velocity in this region. So k, if you want to determine phi, which is how much is the phase difference, you need to know that what is the velocity in this area, in this region, what is the velocity in this region. So the light which is passing through the core and the light which is passing through the cladding, they travel with different velocity, therefore they accumulate different phase. Now since they accumulate different phase, they will going to interfere, and depending upon the condition for maxima and minima, they will form a nice interference pattern in transmission. What you get out here, so at the input end you give this side of Gaussian beam, at the output end, after moving through this PCF, it forms some nice interference pattern. And if you coat this region outside PCF, this is what I'm showing. You see this dark region, dark brown region. If you coat this region with some sort of a nanocomposite of Pani is some sort of a polymer, and SNO2 is an oxide. So if you make a proper mixture of them as a nanocomposite, you can look into this literature, this paper for more details. If you put them suitably around this PCF, then what happens? You please recall that outside this, the cladding mode, different cladding mode will get excited. So N effective changes, and as delta N effective changes, delta lambda will going to change. In the last slide, I showed you that the shift in the interference pattern is dependent upon the length of the interferometer. This is the length, and also what is the delta N effective. So delta N effective in presence of Pani and SNO2 nanocomposite, whenever you put these ammonia to that, they form a complex. So ammonia molecule basically interact with this nanocomposite, and it alters the effective index outside, in the outside region, and as a result the interference pattern going to get changed. So you see, so with on the addition of ammonia, you have something like earlier, when there was no ammonia, you get interference pattern like this. But when you add ammonia, output with ammonia, you see the shift in the interference pattern. Now, this shift in the interference pattern you can monitor. And then if you plot the transmissions versus wavelength for different concentration of ammonia, this is what we are trying to show you. It is 0 ppb to 8 ppb. So the detection limit is close to around 47 femtomolar concentration. Now, these are big numbers in terms of very high resolution. So even if there are very low amount of ammonia, parts per billion or traces of ammonia, one can detect them. Similarly, last was for the environmental pollutants like ammonia. You can also detect water pollutants. This parathion methyl is another chemical which are found in water, and these are uh, pollutants which are present in water. Uh, Only thing is, rather than using a single mode photonic crystalline single mode, here we are just making some sort of a tapered fiber. These tapered fiber are basically a fiber. If you take a glass, if you heat and pull them, then it become thinner in center, and on other side it will be having the same size. So these are thinner region which has been pulled, and you functionalize these region with proper, I should say, with proper complex, so that you are able to detect parathion methyl. So you have to functionalize. So functionalization is important. I have shown you here how these get functionalized. So you coat with something called as a nano imprinted polymer around this, and then you do some sort of a treatment. You wash the probe, and then you get some suitable site here. So whenever you put the parathion methyl here, they will interact with that. So this lead to the change in effective index over the fiber, and once the effective index changes, the modal characteristics changes. And as the modal characteristics changes, there is a shift in the interference pattern. This is exactly what I'm trying to show you here, is that you go on changing the molar concentration of the external media, and you see the interference pattern are shifting. The same interference pattern are shifting. If you plot the concentration versus shift in the interference pattern, you see that it's showing a linear trend, and for a higher concentration, you see it saturates. And this is also obvious that for higher concentration, all the active site, whatever is available for parathion methyl, will get blocked, and therefore there is not much change in the or shift in the interference pattern. We tried to see that whether this will work with other similar type of pollutants, and we have shown you here that we work with uh, parathion methyl, paroxone, parathion, and phenylethylamine. And we realized that only with when you have a parathion methyl, which is the case, you see that the shift is maximum. So this shows that selectively means if there is parathion methyl, then only our probe will work. For other systems, probe will not going to work. Similar type of systems was also utilized for the determination of ammonia, urea. You see that what we have shown here is, again, we have functionalized. These are the different steps, and one can detect urea. So what we are trying to mention here is that depending upon your interest, you can make a device, and that device can be utilized for detection of different type of, detection of different type of biological entity, pollutants. Pollutant can be water, pollutant can be environment. These are all, you don't have to worry, these are all optimization parameter. What we are trying to show you here is it is important that you see, because the polymer that you coat is you coat in different concentration. Please see this graph carefully. If you put your probe for 10 minutes, all the time dipping time is same, 10 minutes, 10 minutes, 10 minutes. So the bare probe shows you the interference pattern. Then this interference pattern, as I explained you, is when the core mode and the cladding mode, they basically interfere, they form some interference pattern. But around that probe, if you put some amount of, chemical, so that you want to functionalize, you see, if you put 3 mg/ml per ml, you are getting, the interference pattern goes away. 2 mg/ml again goes away. One for 0.5 mg/ml for the same dipping time, you see that there is an interference pattern. Now these are all optimization has to be done very rigorously, because if you lose the interference pattern, then the whole idea of making a very sensitive or high resolution device, you will not able to attain. And therefore it is important, then you make a device which is very sensitive. So we are also optimizing the dipping time, washing time. So all rigorous calculation has been done. And same way we try to use with different chemicals, and you see that with different chemicals, only with urea you are getting the maximum shift in the wavelength, and not with other chemicals. Now this was whatever we have discussed was largely either you are trying to address some engineering problem, or you are using some biological problem. Biological, when I say biochemical type of detection, it can be pesticides or water pollutants, or it can be some environmental pollutants. The same system can also be utilized, same system, when I say the same type of optical fiber based systems can also be utilized for uh, healthcare monitoring, human healthcare monitoring. So you see how our healthcare has evolved. So this this shows a typical centralized healthcare facility where you have a hospital and people have to stand up and queue. And this is largely true today also in many part of the country and across the globe, that you have to stand in line, go to hospital. So these are all centralized facility. Now many of you must be wearing a smartwatch, so these are getting more customized, so you don't have to be in the line. You wear them and you can monitor the different physiological parameter. So of course the advantage is these were time consuming and not easily accessible. These are convenient and portable and comfortable. You can wear them and then you can move. Now in future, this is what is expected, that there will be AI assisted wearables. So AI will basically, if you have correct data, experimental data from the clinic, and if you train the AI, it is expected that they will going to give you right picture about the human health. And then you can, using AI, put to these variables, and they will going to give you some feedback. And these feedback can be, obtained by the doctor anywhere in the world at any time, and they can give you comment on that. So rather than centralized, let's talk about variable based system. So a variable based system can be the one which you must be wearing is electronic variable, but in future there will be a variable which are optical variable also. Why electronic variable? Although electronic variable is there are few disadvantages of that. So many a times when you go to a hospital and they show you, they measure the blood pressure and or the temperature, and then you say ki, please can you measure once again, is if it is same. You'll see that the same patient, if it is being measured 2 times 3 times, the reading will going to be different. So that means the output is fluctuating there. Most of the electronic variables, they basically go with intensity interrogation. Basically they try to measure some sort of intensity, uh, intensity, for a specific detection. They want to be, so for, let's say for some case, for some particular ailment, uh, you can measure some parameter, and then the signal is weak. When I say intensity, it is not light intensity but the weak signal. But for other, the signal strength may be more, but then identifying them is difficult. Also they get converted, they may have some problem with the electromagnetic uh, interference, and then a lot of radiations comes out from these electronics, and therefore they may not be very good for skin. If you want to make a sophisticated device or smartwatch, you know that the cost vary from 1000 and it can go to be as high as 2 lakh, 3 lakh. So that depends what type of sophisticated instrument has gone. Therefore these are complex fabrication and can be costly. Also please note, over a period of time you will be creating a lot of electronic waste, uh, and these devices, if you use them every now and then, so due to moisture that you have on your hand by wearing them, these, their lifetime also deteriorates. Also due to this heating effect of all the uh, different circuits that are built there, so they have certain limitations. So some of these limitations, not all, some of these limitations can be addressed by optical variables. You can make it sensitive. Rather than intensity interrogation, you can go for wavelength interrogation. With the same device, you can measure many parameter. This is what here also, you with the same device you measure parameter, but uh, you cannot put your electronic watch around your, let's say, knee or around your neck. It has to be over somewhere. But if you want to utilize them any part of the body, then you have to customize them. These optical variables, especially with fiber-based, waveguide-based systems, they are simple fabrication. They are compact. Only thing is you cannot wear them and walk. You have to wear them at one place and then you can do all the monitoring. So it is wearable, but it is not portable. It is portable also, but it is not like an electronic watch which you can wear and you can run. Possibly that will also come when you have a smaller laser diode integrated with some photodiode, then that problem will also get over. But the advantage is that these you can multiplex, you can do you can have many interrogation systems, and you can do multi-parameter optimization using such type of a system. What will be the impact of AI in the health science? These are all the impact. Now AI is being discussed a lot. So improved patient outcomes will be there, patient data and privacy and security will be there. You can use integrating with AI, you can have easy accessibility to the healthcare services. You can get accurate information, things will increase, efficiency will increase. AI will also help to design customized drugs for the patient and will allow you to have very enhanced patient care. So AI assisted wearables, if you see, can be in this form, right? Wearable device you can have a wristband, you can have a contact lens, you can have a smart cloth. Now, in our lab, we basically work with smart clothing and wristband. Wearable techniques that are used to make wearables can be electronics, can be electrochemical, can be optical. In our lab, we basically confine to optical techniques. Using optical techniques, we do all these type of physiological monitoring. We can monitor the cardiac monitoring can be done. We can measure the sweat detection can be done. Tactile sensing can be done. Real-time body joints bending can be done. Body motion can be done, and body temperature can be done. So what we do in optical wearable device, these are some of the I should say, these are some of the transducer, not transducer, these are some of the platform which we utilized. Either you use grating based system, or you use interferometric based system, or you use some sort of a polymer based systems, and then there are other structures that can be used. Please note the two above are wavelength interrogation and the two below are intensity modulation. So in these two cases, POF based systems and the other structured modulation, you cannot use wavelength based, you have to go intensity based. But using FBG and interferometry, you can make wavelength based. So what I'm trying to show you here is some of the devices which you can make them, and let's not discuss more about how these devices are fabricated, but quickly I can tell you that you have to use some sort of a polymer sheet like PDMS. You have to embed these. At what point you have to embed, you have to optimize them in your lab. And for this particular structure, we realized that if you put at a distance d from the surface, the probe has to be kept in such a way it should be d embedded on the surface and 4d from the surface. Then the optimum performance was there, because you have to worry about the field. So what we have done, if you use this device and if you are place them on human and try to monitor the breathing in 3 of these positions, like normal breathing, yogic position, or running, you see the response of the device. Please note, these are wavelength shift. As I mentioned to you, that interferometric based systems exhibit wavelength shift, and then we try to monitor this. You can count these numbers, and then you will realize that these are same as what the conventional health machines, healthcare devices are providing you. The beauty is, the breathing pattern for all these can be correlated for a lot many other applications or human health identification. The same device, if you see that it has been placed on the ankle, and if you move them, if you bend it, so it not only identify the slow bending, but it also identify the fast bending, how fast you are moving your wrist. It will able to tell you. At the same time, it not only tells you that it also tells you the direction of the bending, whether you are moving up or moving down. So whether it is your convex motion or whether it is your concave motion. So convex motion, you see that it is like this. Concave motion, you see it is like this. So the speed, then the direction, both can be determine using such type of probe. For especially for surgery, especially for applications where plastic surgeries are done for human, mouth bulging is an important aspect. And then you can see that opening and closing of mouth has a different signature, what it has shown here, and it can be utilized to identify that. The same probe can also, this is what I was mentioning, that you cannot put a smartwatch cannot be put around different parts of a body, but a customized optical probe, what we develop in our lab, can be put in different part of a body, whether it is on wrist or whether it is on your mouth, or whether it is for to determine the blood pressure or pulse monitoring, all can be done through the same probe. Then you have, I guess this should work. So this is the video which you can just have a look at. This video. What it is showing you is some human. You can see the hand movement of the hand here. You will realize that how these signals are being, how these signals has been taken into consideration. So you see the movement of the wrist. So any wrist bending you see, whenever this human will move the wrist, there will be a line that will pop up at the top. What I'm trying to tell you is that these have quite a bit of commercial potential, because when we compared our device, this is our proposed device is green one, commercial is the red one, on 3 different human subjects, I mean 3 different human being, and try to measure the heart rate for all. For all that, the heart rate was similar to whatever is commercially available. Now, the commercially available, of course, is based on electronics. What we are trying to do is based on optics or photonics. Advantage is these devices are reconfigurable. When I say reconfigurable, you tell us that how sensitive or what is the resolution you are looking for, we can make it. And these are also scalable. One device can make many measurements. This is a beauty. Also, these are not very costly, and depending upon the users, you can also tailor the patch size as per the requirement. And in some of the cases which I have not discussed here, these plots are better than the plots which you get from systolic and diastolic peak. These are systolic peak, these are diastolic peak. It is better than the commercially available device. And these peaks, whatever you are showing, gives you much more information about the human health than only the systolic and diastolic peak. This is what you can see here. This is a peak. This is a PPG which are available in the market. These are piezoelectric based, again available in the market, and this is our system. So these two systems are enabled to identify the 2 human peaks. So these peaks are basically the tidal wave, or these are called as a dichoric peak, or this notch is called as a dichoric notch. So they tells further more information about the human health. Okay, so what we visualize that you have some physiological data from a human being. It can have optical signals, historical data about the human health, data for long term, whatever the data he has. They can be pre-processing of data can be done using AI for by doing denoising, data transformation, feature selection can be done, as you know that AI gives you this, and then dimension can be reduced. You can train the AI using one of the model like neural network or vector machines, decision tree can. These are different models which are available, and then you can interpret the result. So you can, from the result, you can get your daily health monitoring, diagnostic aid, or some early intervention is required, or some sort of a pandemic tracking can be done using all type of. So you can put these variables, optical variables, on any different part of a body, and then you can monitor all this part in real time. What we visualize, this is how the futuristic AI variable will be there, that you wear one of these things through all these different platform. These data will be transferred to one of these smartphone, personal laptop, Then it will go to this cloud multiple tenant access control where private database will be there. These data will be again processed, will be shared to database. Then it can go to the medical data attenuation. Again, you have some global data. Again, you open this data set and then you annotate those data. After annotating that data, you use what is called as a clinical decision support system, and then you map them, and then it can be given to the hospital, and then it can again from AI data, whatever is available, it can be matched, and then the diagnosis or treatment plan can be sent to the patient. Okay, so another part which is more from a aerospace engineering or micro crack monitoring, how it can be done. It can be done using again making some sort of a cavity. This is a simple equation. You have some sort of a micro air cavity. You can visualize this cavity like some cavity like this. And if you incident a light, this D will going to change. So this major and minor axis will going to change if you pull this sphere. You think that if you pull this ellipse or if you compress this ellipse or pull this D will change. And as D will change, the delta will change. And as delta will change, the interference pattern will change. So you will have some interference pattern like that, but this can be changed by changing the D. So what we created is different type of cavity, which we say micro air cavity on demand. You make any type of cavity depending upon how sensitive you want to make the device. Then we also try to make two cavity in the same optical waveguides, optical fiber. We make two cavity so that you can monitor at two different location, and we try to see that such type of cavity can be utilized to detect micro cracks in the bridge. These are some FFT that has been done. You don't have to worry. But only important aspect what I'm trying to tell you is, you see these are air cavities which are very prominent. So whenever there will be some cracks and stuff, you can see that these things will going to get rise. So you can identify them using some hybrid cavity. What are the modes that get there? So that will help you to identify the cracks. One can also do dynamic monitoring in real time using specialty fibers. And then you see that if some structure is vibrating at different frequency at the same time, for example, 5 hertz and 10 hertz, 10 hertz and 5 hertz, or 5 hertz and 100 hertz. So these are all problem related to engineering. If some structure is vibrating at different frequency, you can identify all those frequency like we have shown you here: 5 hertz, 10 hertz, 100 hertz, 500 hertz. So all these are experimental results. These can be identified. There are another technique which people say as a noise cancellation. So suppose your sensors is very, very noisy, it is not able to resolve. So in order to make high resolution sensors, you can put them in parallel. You can put them in parallel, you can combine them, and then you can do, some sort of a cancellation. So these are all very advanced. These are all very advanced monitoring systems for, you can say that, for industrial plant where you have you want to monitor the performance of the some parameter in real time, and that noise that is coming from those parameter are very too much. Then how to reduce the noise can be done using parallel interferometric concept. Another part of the topic where parallel interferometric is by doing the smart traffic monitoring, that you embed your sensors, these high resolution sensors on the road. And then these are what I'm showing you. These are sources, these are detectors or DAQ. You have two probe, and then using them, you track one of these peaks. You see that it has been tracked over time. You don't worry about that. And one can measure the load sensitivity of 40 kilometer per, for 100 kg. So important result is shown here. So if you see, if you have a bicycle guy with a bicycle, we have intentionally, we have tried to blacken this. So for bicycle, you see the signal. What is important here is delta lambda. What is important here is delta lambda for car. What is important here is delta lambda for motorbike. What is important here is delta lambda for bus. The delta lambda for all these are different. Not only delta lambda, but also if you see the width, this length for all are different. This length for all are different. So this technique can be utilized for traffic monitoring in smart cities, and it tells you not only about the nature of the vehicle, it also tells you about the load of the vehicle. So this is what I'm trying to tell you, analysis that has been done, again taking help of some of the some of the AI tool. So it tells you by measuring these are sensor reading in picometer, these are weight of the tire. So by measuring the weight of the tire, you can tell them whether it is car, man, human, bike, or bus. And also the total load can be measured. So you can tell the velocity of the vehicle, you can tell the type of the vehicle, you can tell the tell whether the vehicle was uh, four-wheeler, two-wheeler, nature of the vehicle, velocity, nature of the vehicle, uh, then type of the vehicle, and also the direction from which vehicle is coming. If the vehicle is coming from a wrong direction, that can also be identified. And if also vehicle is having a overloading, then that can also be identified. So these are this is some analysis that has been done. You don't have to worry. So by calculating, you see that what we are trying to calculate is we are trying to calculate the speed of individual vehicle. If the bike was moving at 7 km/h, the wheelbase length of the bike was this, and the wheelbase length of the bike was this. So the two bike having different wheelbase can be utilized to identify. Okay, so that takes us to the quantum part. What we have been discussing till now are all classical in nature. Those are all classical. What we'll be discussing now is little bit of quantum. Uh, but in quantum sensing, people use different type of platforms. Please note, quantum sensing is, quantum sensing means, again, please note for any sensing you require three parameter: light source, the sensing unit, detection unit, and the data processing unit. Now, the one that you are seeing here, you are seeing here is basically some sort of a very advanced technique what people use as a defect in diamond. These are called as N, V center. You see, these are N, these are V, and this is what complete you are seeing is some sort of a diamond structure, and inside that you have some defect. So what you do, you incident a laser radiation. You also wave incident some microwave radiation, because the resonant frequency of these defects is around some microwave regime of 2.87 gigahertz. And you put these defect something near like this, and you incident a light, use diachroic mirror, do the processing and stuff, and you can identify. You can, using CMOS camera, you can identify temperature, or you can identify magnetic field sensing, very high, very precise temperature or magnetic field sensing of order of some femtotesla can be done by integrating these NV centers with the system. Another area what people have been doing is putting the quantum emitters on some optical nanowire. So this is an optical nanowire, these quantum emitters. Now these quantum emitters can be any type of quantum emitters. When I say any type of quantum emitters, I basically mean these quantum emitters can be semiconductor. These quantum emitters can be NV centers. These quantum emitters can be colloidal quantum dots. So any type of quantum emitter, you put them, and you try to interface these quantum emitters on this nanowire. You excite them suitably using some lasers. This quantum emitter will going to emit some single photon. The single photon get coupled to these optical nanowire, and you can collect this single photon and do the correlation study to identify whether these are single photon. And once you have done that, you can again utilize them for magnetic field sensing. This is, this is, as you can correctly identify, these are some sort of interferometric setup, and I have discussed with you that they utilize the concept of SPDC, spontaneous parametric down conversion process, to generate single photon, correlate them, and then you can displace the one which you are interested to sense. You can displace by certain distance and you can monitor them. So these can be utilized for object identification or dynamic motion sensing. This can be utilized for. So this is another picture. What I have tried to show you is, if you have a diamond and there are some vacancy, either it can be silicon vacancy or nitrogen vacancy, that can be utilized. Let's not go into the working of how these happens, but what I can show you here is something interesting that you see this. If you take the PL intensity of these NV centers and plot with the wavelength, you get NV0 and NV minus. This is a nitrogen vacancy. Now these nitrogen vacancy are the one, so you have to remember that the NV center excitation line 6 is 637. And this is NV0 excitation lines, PL intensity you get at around 575 nanometer. Now, what happens if you put these NV centers inside magnetic field? So the transition, you have to be careful here. If you see this diagram carefully, this is a ground state, this is excited state. For ms equal to 0 to ms equal to plus minus 1 and ms equal to plus minus 1 to ms equal to 0 for the ground and excited state, you do the excitation, it comes back, and then it gives you it releases some sort of a photon. Now the point is, if you have no magnetic field, as I was mentioning you, this is 2870 megahertz, which is 2.87 gigahertz. But if you apply the magnetic field, the ms plus 1 lines get splitted. You know from our basic physics that under the influence of magnetic field, Zeeman effect, you know that. So these lines get splitted into ms minus 1 and ms plus 1. Now, this splitting of the lines can be correlated to the amount of magnetic field which has been applied. Now, these amount of magnetic field are really low. When I say really low, these are of order of picotesla and femtotesla. So people have utilized to do a lot of magnetometry using nitrogen vacancy centers. People have done some magnetic sample. They have done, so there are different types. This is something which we have also done in our lab. And now it is published. You can have a look into that paper. So what I am trying to tell you here is as follows. If you want to make a very high resolution sensing system, then there are different techniques. Now, as I mentioned to you, that the most sensitive technique, whatever we have, optical is one technique which is very, very sensitive. Now, when I say that optical is one technique which is very, very sensitive, I have mentioned to you that these optical techniques, the one, for example, is LIGO, is one technique which are the most sensitive device, or the most device with maximum resolution that has ever been made by the human being. And therefore, in today's talk, what I try to confine tells you that how these optical techniques, whether it is interferometric or plasmonics or optical based quantum techniques, can be utilized to develop sensors which can give you very high sensitivity and very high resolution. In this whole discussion, what I try to discuss with you, that how can you make interference, how can you create interference pattern using optical fiber as such. You can also create interference pattern using bulk system, like you have a beam splitter, you put the you incident a laser light, and then you have two arms, you try to put them on a screen, then you use some sort of a diode some photo detector to map those, interfere them, and you can map them. But the whole idea is these become very bulky, so you have to put them on a optical table and then you have to do these experiment. People also does that. What I'm trying to impress upon you today is that we utilized optical fiber. Now, a conventional optical fiber, if you taper it down, it excites the cladding mode. So as you know that for to generate interference pattern, you require two beam. So one is my core, one is my core mode, two beams, or here we are saying two modes. One is my core mode, which propagate inside the core, and another is cladding mode. So if I can generate cladding, different type of cladding mode, and this cladding mode can interfere with the core mode, or there are some fibers where you can have more than one core mode also. So the idea is to interfere core mode with the cladding mode, or core mode with the core mode, or core mode with the higher order core mode, higher order core mode with the cladding mode. So there are different combinations to do that. And you can lay these combinations to form Michelson interferometer, Mach-Zehnder interferometer, Fabry-Perot interferometer. All these different type of interferometer can be made using these optical fibers. And if you can functionalize these interferometer, optical fiber interferometer, using suitable advanced material, for example, Pani and SNO2, optimize the dipping time, elution time, washing time, all these process has to be there to optimize them. So if you can optimize them suitably, and then if you put ammonia, then the core mode will be same, but the cladding mode effective indices changes. Since the core mode, which was core mode and cladding mode, which was interfering to give you interference pattern without the addition of ammonia, will be different now. Therefore, the interference pattern shift. Please also recall that I mentioned to you that the shift in the interference pattern depends upon the length of the interferometer, and it's also depend upon the effective index difference. So as soon as you put ammonia, the effective index N core minus N clad changes. As it changes, the shift in the wavelength changes. As the shift in the wavelength can be plotted with the different concentration of ammonia, you can identify the different concentration of ammonia. Through this, you can make a very sensitive device. The ammonia concentration of femtomolar and picomolar concentration can be utilized. Similarly, you can make different type of probe for pesticide detection. Like I discussed with you that how can you determine marathon, methyl parathion, which is a water pollutant. Ammonia is an environmental pollutant. What I'm trying to tell you is you can make a very sensitive device for water and environmental pollutants. The same system, if you can put them suitably inside some polymer, can be utilized for human healthcare monitoring. Now, when I say human healthcare monitoring, I basically mean that these are variables which you cannot run with these variables, but you can sit and then you can at one place you can put in the hospital or you can put in your home. You take the source and detector, and different patches can be utilized for different disease identification of different tests. So you can measure the respiration rate, you can measure the heartbeat, and these will be very useful for elderly people, elderly, to take care of the elderly people, and also for athlete training and rehabilitation. These devices can be also integrated with cloth, so that you wear it and then you can monitor the different part of the body, you can monitor them possibly. If you make these interferometer in a cavity form suitably, then these interferometer in a cavity form, if there is some crack in the bridge, the cavity will change. So cavity will change. That means the light which will get reflected from the two part without crack and with crack will be different. That difference will be reflected in terms of the phase difference that is there. That phase difference can be mapped to the interference pattern, and then you can make out that what is the crack that is there. All these systems can also be integrated to AI, and these AI integrated system, apart from healthcare, can also be utilized for either aerospace monitoring or for smart traffic monitoring, where I showed you by suitably making the device, embedding them on the road, you can monitor the speed of the vehicle, the type of the vehicle, the direction of the vehicle, the weight on the vehicle with the same device. So all these are classical picture. But if you have to make, please note, even if you monitor the temperature or magnetic field using any of these device, then the type of number that you get is not comparable to the type of number that you can, or the number that you get using, let's say, quantum systems. One of our quantum systems is NV centers. Using NV centers, the type of magnetic field that what you can detect is of order of femtotesla, which is not possible. People have reported something like micro Tesla using the classical device, but using quantum device, femtotesla is possible. Also, with the quantum-based thermometry, it is possible. It is possible to do. This is what we have also demonstrated in our lab, to especially resolve 2 points separated by 200 micron. If the temperature between the 2 point is less than 10 to the power minus 2 degrees centigrade and they are separated by 200 micron, we can resolve them. So the beauty of these comes from the quantum nature. And I try to impress upon you that why we are able to detect so precise magnetic field is because under the influence of magnetic field, the ms plus minus 1, they split, and this splitting in the magnetic field happens around 2.87 gigahertz. So you can characterize these splitting in terms of the magnetic field that you have incident for the development of magnetometry. So with this, I will say that thank you very much for your kind attention, and I will be happy to take few questions before we go to the next session, where there will be one problem of, how one can make these uh, interface, especially optical nanowire interface for adding these single quantum emitters, and how these can be, how one can measure how much single photon will get coupled to these optical nanofiber interface. We'll be taking up in after the small break, but before that, please let me know if there is any questions. Thank you. Yes.
There is two discussion type questions are there. The quantum systems are prone to noise affecting accuracy. Then how much it's useful in biomedical applications?
Quantum systems are, can I see these questions?
Yeah, yes. In the chat box you can see.
I see. It's opening. Yeah. This is Sankar P. Quantum systems are prone to noise affecting accuracy. Then how much it is useful in biomedical? Yes, this is a good question. Noise is a big challenge in quantum systems. But when we are talking about the comparison with the conventional classical systems, what exists, it's again has far better result than the classical systems. But if you want to go further deeper to be, to customize these systems for something more sensitive, then of course noise cancellation will going to be different, or it will be going to be slightly difficult to handle. So I think I will say that noise cancellation in the present scenario, whatever classical system we are using, we can have a better systems based on quantum for high resolution sensing, but noise will be there. So how to cancel the noise is something a different challenge, but it is good. It is good that you have raised this question. What I will say you that, especially for example, for these magnetometry applications, that MRI use these magnetic field. For imaging they use uh, for imaging different part of a body, they require some sort of a magnetic field. Now if you can precisely want to determine, let's say, something which classical system can image, so you can go for a very small field and still you can able to image them. So body need not to be exposed to high magnetic field is one. Another thing is for if you have to really do much, if the noise is too high, then you can increase the value of magnetic field to get a better signal to noise ratio. So these advantages will be there. These advantages with the classical system will definitely be taken care by utilizing the by utilizing the quantum systems. So noise, to start with, it's all depend upon how precisely you want to monitor. But with the current system, whatever we have, the quantum systems will going to give you a much precise, or will give you high resolutions as compared to what the classical system can provide. Quantum results are hard to interpret in biological. I think I have addressed this part. Can we use any algorithms or for enhancement? Uh, Algorithm, Srinivas Raoji, what do you mean by algorithm? For which enhancement you are talking about? And can we use any algorithms, sir, for which enhancement you are talking about?
Yes, Srinivas, you are mute. You can write in the chat box because for you that the algorithm part will be discussed by Tarun Datta on 27th Feb. So if you are any specific, you can ask the speaker. Otherwise, it will cover on 27th Feb.
There seems to be no question. So we are now at 4:30. So maybe we'll take 5 to 7 minutes break, and then we can have a small quick session how to model a problem which can be solved using quantum. Is it okay?
Yeah, sure, sir.
Thank you. Thank you. So, but that will be from a different laptop. So please allow them. I will have to go to the lab for that. Okay.
Okay, no problem, sir.
Okay.
You can
Okay.
save ID.
Thank you. Thank you. Thank you. वाईफाई पे शेयर है क्या इसका? Am I audible?
Yes, sir.
Yes, sir. Loud and clear.
Okay. Okay. So this will be a small session, and one of my PhD student, now he is a postdoc, Dr. Subrat Sahu. He will be in 20 minutes. He will just briefly explain how we can take a one quantum systems and how we can integrate some quantum emitters and how we can collect the single photon. So I will give it to Subrat. He will going to share. Okay.
Yes, sir.
One second. बात कुछ बोला हुआ है। और कुछ बोला है क्या? इसमें से क्या? और सब।
Yes, my slide is visible to all.
Yes, slides are visible and are in presentation mode. All good. You can proceed.
Okay, thank you. Good evening, everyone. I'm Subrat Sahu, working with Professor Rajan Jha, sir. So, as the sir have given a brief, like extended details about the quantum system using optical fibers. So, this is the schematic of the optical fiber, as sir already explained, which contains a core, clad, and a outer jacket. So, this optical fiber have different working. Uh, uh, Optical fibers have different like application from starting from communication to sensing flexible. So in all this system, one thing is better how the mode is propagate in the fiber and it can interact with the surrounding medium. So as can be seen this left hand side, so this system is a single mode fiber system where the when you purchase a file of a fiber of single mode fiber, it contains a core and cladding. So so as can be seen, the core at the core mode is propagated inside it. So when we go for the optical nanofiber system for the quantum applications, in this case the core, the whole system that reduced into a nano waveguide system, as can be seen in a single mode fiber. The core is 9 micrometer, cladding is 125 micrometer. However, in case of a optical nanofiber, the core is reduced to 300 nanometer, and the outer side it is acting the it is the air medium. So as can be seen, there is a strong field confinement can be realized for the optical nanofiber. One can also visualize from this figure like this electric field distribution also, where in case of a single mode fiber the mode is only confined into the core, whereas in the optical nanofiber it coming outside of the system. So how we can design and simulate the field profile of the optical nanofiber based system. So this is basically the step by step procedure where we first design the geometry, then after designing the geometry we will give the material of our interest, like if it is a fiber it is of silica material, and if it will work in different materials, so we have to give the material property to that. Then we'll give the simulation region and meshing. This part will work for the, like you have to reduce the the total geometry into smaller parts. So the here we basically do the Maxwell's equation solving. So here the meshing region act Maxwell's equation in a small part. Then after the simulation, it can again combine all these things, and at the output, it will give the result. Then we have to define the source and monitor how it can, the light is injected in the fiber, and at the monitor we will see how the outer profile will look like. Then we'll run the simulation, then we'll get the output. So here is basically some fundamental of which I have already explained. So as can be seen, the fiber is like 1,000 times less as compared to optical nanofiber, is the 1,000 times less as compared to our human hair, whose diameter around 300 nanometer, and it can the field coming out of it can go. And here it can also work for the quantum system, like it can support. If you place a quantum emitter on it, the emitted photon can easily go inside it. So this is the field profile of the optical nanofiber. As can be seen, it is the field coming outside of the fiber, and these are different modes of the optical fiber component. That is the X component, Y component, and Z component. Now coming to the like the real quantum system, what sir already explained. Here we have taken a optical nanofiber with quantum emitter. With like when we excite the quantum emitter, the photons are coming out of it, and a part of the photon goes in the guided mode into the fiber, and rest of other goes to the uh, radiation mode. So from this we get the Purcell factor. So how much enhancement one can get in the when the quantum emitter placed in the optical nanofiber, and from the coupling efficiency we'll get the how much photon is coupled into the system. So in the simulation process, we will take the quantum emitter as a electric dipole. So as can be seen, the electric dipole as a quantum emitter, when it radiate, the emission goes into the fiber guided mode. So this dipole source has three orientation. One is the radial orientation, another which is like perpendicular to the fiber, azimuthal orientation which is tangent to the fiber, and axial which is in line with the fiber. That is it is uh, it is parallel to the fiber. Now here we have calculated the coupling efficiency. Now we'll start the simulation process. How one can get this parameter like the mode and the coupling efficiency from the simulation. So let me share it again on the simulation one. Wait a second.
No, you are connected, please. Hello.
Yes,
Yes.
I'm
You are
sharing.
connected. Yeah, please
I'm
share.
sharing. So is the window is visible? Hello, sir.
Not now. You are sharing a multiple screens. You have to open
Oh.
that screen you want to share. Just open that screen.
Let me share it again.
You selected the whole
Yes.
screen.
Now is it visible? Now
Yes,
is it visible?
Visible. Yes, visible.
Okay. So
Please.
this is the we are using the FDTD simulation, that is the finite difference time domain simulation. So which can solve the Maxwell's equation to give us the result. But we have already discussed in our slide. So this is the window of the FDTD simulation, where we have to first from the structure we have to make the geometry, and here then we have to give the material to it, and we'll give the simulation region, source, monitor, then run. The procedure I have explained in the later slide. So let me so the first I have to design the geometry. So as the fiber is considered as a cylindrical geometry, first I have to uh, choose the circle. So you can see the circle here. So for our convenient to see the how the fiber is oriented, I have to change the geometry uh, so as I have explained, the fiber diameter is 300 nanometers. So the radius is 15, uh, like 0.15 micrometer means it is 150 nanometer. Then I have to take the span as 0. So as the material I have explained, the fiber is a silica. I have to choose the material as silica. That you can see the SiO2 silica glass, and the rotation I have to make it 90-degree. So you can see that this is a cylindrical circle. It has the all the different views, xy, xz, and yz, and it is the perspective view. You can see it here, from the system, you have to you can see it is a cylindrical geometry with the extended version. Then we have to give the simulation region. So this is the orange one is the simulation region. So we have to do all the simulation within it. So we have to rearrange the structure. It is 0, 10. So you can see we have already defined the geometry. Now the next job is to select the source. So we have to take a mode source, because this mode source is supported by the optical nanofiber. So we have to place it properly. Uh, so let it be minus 0, 1. So I have give my source here, and this side, the input side, I put a source. At the output side, I will place a detector to detect the what is the signal coming out at the end. So you can see that I put a source here, and at output end I place a detector. Now I will go for the simulation. So now I have to save it at a proper place. I give it as ONF, name as ONF. So now we are submitted our job. The simulation is going on, like the live simulation. It will take a bit of time. So this time simulation time depends on your simulation region. So as the simulation region increases, it will take that much time as well as the space. So to perform this type of high performance computing system, you have to have a good computing facility as well as uh, the configuration should be small. So as can be seen, our simulation already done. So now we'll go to see the how the results are look like. So first I visualize the electric field. So one can see that there is the electric field shown here is the total is the so this is the electric field of the system. So this shows a blurry type of things because the mesh we are choosing is so much lower. So if you take a mesh like, let me do it again for better visibility. So here the mesh accuracy is 2. Now if you make a so it will take a bit time, so I will not going into that direction. So let me shorten the length so it will make it quickly. So let me do it in the like 2 only, so I will go move forward with the slides. So okay sir. Okay, और 2 minute. So it can be seen the like the E electric here, and it is the EX is the X pole component, Y is the Y pole component, and it is the Z pole component. So from this we can visualize the electric field. Now we'll go for the how the quantum emitter is interact with the system. So in the same system I am choosing it is disabled. So I am choosing a dipole source. As I have already explained, the quantum emitter is considered as a dipole source. So I have to place it properly like it is. So it is 0. So I have to take it 600. So as can be seen, so here I have put a quantum emitter here on the top of the optical nanofiber. Then I go for the simulation. So after the simulation, we have to like analyze the result. Like from the source, we can get the Purcell. So we get the Purcell factor around, if you see the Purcell factor around 0.73 for a particular wavelength, and a part of light can like couple into the fiber system if we like take the transmission of it. So how much it get transmitted, one can see 0.09. So out of 0.7, it part of goes in this direction, 0.09. The same thing you can see also. So it is also 0.092. That means it is a symmetric coupling. The emission from the quantum emitter equally couple into the system. So this is all about the how a quantum emitter couple into the optical nanofiber to channel the single photon coming out of it into the system. We can numerically analyze it. So if you have any question, you please go through. I'll happy to answer. Hello.
Yes.
Yes.
Hello, sir. Uh, like if you have any question, I will happy to answer.
Okay. I request participants. Please post your any queries or questions if you have.
You can see the chat box directly, speaker, so that you can directly answer. I will read for you one question. There is a parallel visualization is possible in this or not?
Yes, yes, sir. If you read out the question, I will have easy to like give the answer
Okay,
from the
he
chat
is
box.
talking about that parameter visualization in this.
The parameter visualization of the system,
Yes, sir. Mr. Shankar is asking about
like
that parameter
parameter
visualization is possible or
like the parameter visualization, like we have to give the parameter first, then we visualize the result. Like here I have uh, uh, like define my parameter. The radius is around 300 nanometer and the wavelength I have chosen, it is around 600 nanometer. So in this case, the optical nanofiber case, we have to choose the diameter of the fiber is half of the operating wavelength. Like the wavelength I have chosen 600 nanometer, so the fiber diameter I have chosen as 300 nanometer. So like answering to your question, parameter visualization, uh,
yes,
I
that
like
is
if
not
you
the
clearly
direct question. Please, Mr. Shankar, can you please specify what you're talking about? You are talking about parameter analysis or
unmute.
something like that?
Exactly. If you please like directly ask the question to me, it will be better to answer your
He
question.
is talking about coupling efficiency.
Yes, yes, yes. Of course, like the coupling efficiency, the if you see the monitor T, so the like you can note down it. The T is 0.09, 09, and as the on both side the monitor it is 0.09, so it is 0.09 into 2, and the from the source we have calculated the Purcell factor, so which is around uh, 0.73. So if you calculate that, uh, you can get your coupling efficiency like 0.09 into 2 divided by 0.73. So you can get around like 24% of the coupling efficiency into the fiber guided mode. Like if you do the mathematics, you will get around 0.24. So if you like multiplied by 100, so you will get the answer in the percentage. So you will get 25% your emitted photon that is coupled into the fiber guided mode. I think I have answered your question.
Yes, sir.
Yes, yes, perfect. So any other queries? So I could not see any other queries. So let us thank the speaker Professor Rajan Jha, and you also for taking this short session for the demonstration. So now we are closing
Yes.
our
Thank you for the
fourth.
opportunity.
Yeah, thank you. So we are closing our fourth day this faculty development program on quantum sensing. Once again, I thank today's speaker, Professor Rajan Jha from IIT Bhubaneswar, and all the participants for joining today. Again, please keep posted your queries, and we are scheduling the quiz on this Friday, and today's will be given, and you have to submit it. So please be ready for the quiz by this weekend. So we look forward to see you tomorrow for the next session. Once again, thank you all.
Thank you.